Innovation and Design Thinking. IDT. Module 2. Tools for Design Thinking. Case Study. An instrument for real-time design interaction capture and analysis. By J. Babu. Tools for Design Thinking. An instrument for real-time design interaction capture and analysis. This is a research work conducted by Matthias Afflacker, Thomas Covert, and Alexander Zayer. This video presents key points from their research work. It is incontrovertible that communication plays a central role in collaborative activities such as engineering and design. The success or failure of complex projects is considerably determined by how design teams communicate and interact to request information, negotiate, generate ideas, make decisions, or resolve conflicts. Acknowledging communication as an influential factor that determines team performance, communication behavior should be made measurable in order to establish deeper insight into what characteristics are beneficial or detrimental for success. However, new techniques are required to efficiently study team interactions during the early stages of engineering design projects. The augmented virtualization and geographic dispersion of team environments raises demand for an adaptive, computer-supported design research methodology, which takes the increasing role of online communication into account. The Design Loops project develops new technology to instantaneously collect and process arbitrary team interactions in the course of virtual collaboration. In the effort to construct, apply, and evaluate an automated approach to design team observation, the work gives answers to the following research questions. Research question 1. How can design team interactions be chronologically modeled and represented in a computer-processable format? The formalization and recording of activities under observation is required for computer-assisted team collaboration analysis. The initial research objective is to find a suitable data structure that can keep a temporal representation of the identified collaboration qualities. Research question 2. What are the structural and dynamic properties of a software system that facilitates the real-time capture and analysis of design interactions in a technology-enabled environment? The second question is about the architectural arrangement of a software system that will handle the formalization process and give real-time data inspection capabilities. Multiple workstations spread across time and place, concurrent team interactions, and a wide range of media and groupware for virtual collaboration all necessitate a scalable solution. Service orientation is an architectural paradigm that promotes integrability, flexibility, and reusability in distributed and loosely connected software systems. The creation of a service-based software system for performing computational observations and analysis in dispersed and heterogeneous design settings is a new path in design research. What is the nature of the services to be provided, and how can such a system be integrated into the design process? In the background of these research questions, the following hypothesis is being formulated. Hypothesis of this study. Online interaction signatures of high-performance design teams are significantly different than those of low-performance teams. Finding strong correlations between aspects of formalized interactions and independently measured team performance is a required, but not sufficient, condition for the computational evaluation of design process qualities. The presented technique would suggest itself as a foundation for a design management dashboard to monitor those indications in real time now that the first signs have been revealed. The Design Loops project included a significant portion of testing this concept. The results of a case study analysis are presented at the end. Improving design process instrumentation. The growing availability of software services For computer-supported cooperative work, CSCW, and virtual collaboration has altered design environments and people's communication and sharing of information. The Internet and the World Wide Web have shifted groupware applications, giving an open interface for connecting people and information. In fact, especially in worldwide enterprises, communicating over the Internet has become routine and vital. Web 2.0 services and other forms of communication, such as instant messaging, are becoming more common in the workplace. Using web platforms to store and distribute project data provides an unprecedented level of information accessibility. Although previous design research has increased the assessment and transparency of performance-relevant process variables, instruments to evaluate computer-mediated team activities in real time remain uninformative and fragmentary. This work developed the same. Can digital traces of communication be a surrogate for team behavior? The concept that low-level data at the technical level of communication can be a proxy for the original goal of an encounter is central to this work. The relationship between online communications, structured encoding, and its semantic significance in a collaborative environment is mostly unknown. The nature of communication itself is at the base of this issue. It is classified as a semantic problem by Shannon and Weaver in 1949. How precisely do the observable symbols transmit the intended meaning? See the figure 1. This figure shows the communication model proposed by Shannon and Weavers can be utilized to sketch out a non-interfering approach to communication capture. While there is valid criticism of this model's static and linear nature, its technical bias towards discrete pieces of information is manageable because computer-mediated communication activities are the only ones targeted. A software system, encoder, digitally encodes data and sends it to a receiving software system via an unspecified data connection, channel, decoder. Each of the three entities is a potential source of data for documenting team interactions. Public interfaces, log files, or other traces of contact may be used to unoppressively tap into the information exchange process, depending on the transmitting and receiving software systems. Recent research suggests that data at the technical level of communication could be an observable substitute for a message's semantic aim. The topic of whether and how data in the form of recorded interactions could eventually serve as an indicator for differences in design team activity and innovative performance is to be answered. The envisioned instrument would qualify as an upgrade to design research technique if dependencies between observable patterns in team communication and objectively assessed features of a design process could be identified. This background is used by the authors to develop a real-time design instrument. A real-time design research instrument. Matthias Afflacker, Thomas Kowerk, and Alexander Zaire developed an extensible software architecture of networked and loosely coupled sensor and monitoring components to enable real-time communication capture and analysis capabilities in real design contexts. During the process of cooperation, a set of software services provides the capabilities needed to incrementally capture and query detailed communication properties. This creates a single point of access to information on how design teams communicate virtually across time. Computer-mediated team interactions are necessary, common, and widespread in technology-enabled, distributed engineering design spaces. The symbiosis between design practice and research is facilitated by this service approach to communication collection and analysis. See the figure. The system serves as a data collection tool for design researchers. A variety of client apps can check for digital traces in the communication channels on a regular basis and feed information about captured interactions to the services. Simultaneously, the services enable users to analyze trends and characteristics in recorded occurrences, as well as to systematically investigate the history and present of communication behavior in observed teams. New theories in conceptual design process can be established and evaluated, resulting in a better knowledge of important team communication metrics. After the symbiosis is complete, the set of services can be iteratively modified and adapted to provide better advice, management, and design process assistance. See the figure. Figure shows the capturing the design team activities. A critical first step in the analysis is the creation of an acceptable data model to describe the individual communication activities of design teams. TCNs, Team Collaboration Networks, are a graph structure that represents the presence, attributes, and relationships of diverse actors and information objects during the duration of a project. Figure shows an example of a team collaboration network with 4 nodes. Persons A and C are represented by nodes A and C, respectively. B represents an email sent by a person, while D represents a wiki page produced by person C and referenced by email B through a hyperlink. The model structure keeps track of prior network states and ensures that cooperative activities can be traced. The examination of earlier interaction behavior becomes possible in this approach. System implementation and test-bed integration. Authors then created Design Store, a resource-oriented platform for team collaboration networks, as a second phase. In heterogeneous groupware applications, the system provides a rich API for the ongoing recording and evaluation of virtual collaborative activities. The services were utilized to collect interactions through email messages, wiki pages, and online shared folders across an 8-month period of early-stage concept creation in 11 engineering design projects. The produced networks serve as a starting point for investigating communication structures. The platform was tested in a project-based engineering design program. See the figure. Figure shows Mechanical Engineering Project-Based Engineering Design, Innovation and Development at Stanford University is a 9-month graduate engineering course in which Stanford students collaborate with students from other universities around the world to develop innovative solutions to open-ended problems. Industry partners presented small scattered teams with real-world engineering design challenges. The design tasks were written in a wide manner to encourage students to identify, isolate, and explore a specific potential for innovation. Figure shows the overall layout of engineering design projects during the 2007 to 2008 academic year. A total of 11 teams were established, consisting of Stanford students and students from 6 partner institutions across the world. Stanford engineering graduates collaborated with students majoring in product design, industrial design, or computer science to develop cross-disciplinary problem-solving and teamwork. The team was made up of 6 students, with 3 students representing a co-located subteam on both the Stanford, local, and worldwide partner sides. Each team had an equal amount of money to spend on materials and services, as well as to create prototypes. A design task was assigned to each of the geographically distributed teams via a business liaison. Throughout the course, the students were required to collaborate in order to discover needs, produce concepts, and create fully functional prototypes in order to demonstrate to the corporate sponsor a feasible road to innovation. The project schedules are divided into 3 primary phases, each lasting around 3 months. The first phase, Make It Up, begins with team building. Local and global subteams meet for a brief kickoff session, and is marked by a high level of benchmarking, fact-gathering, and brainstorming activities. The second step, making it real, focuses on the student's vision's technological viability, as well as the implementation and testing of their ideas. The third phase, make it happen, focuses on completing tasks, making final decisions, and delivering a working solution at the end of the project. Case study in team performance management. In unstructured contact and virtual design collaboration, the Design Store platform enables concentrated observation of specific communication aspects. This feature has been used to closely observe specific trends in the captured activities of the test-bed projects previously discussed. Statistical associations between observable interaction features and team performance metrics are investigated in this case study. On the team distribution lists, we have over 10,000 emails, over 800 wiki pages with around 4,000 edit events, and over 8,000 activity in public team folders. A number of performance measurements were empirically collected from the teams to investigate dependencies between online interactions and performance-relevant process parameters. Self-reported performance metrics were questioned after the projects were completed to quantify process performance from the designer's perspective. The questions are drawn from a well-known team diagnostic questionnaire. They give a measurement of 3 performance-related dimensions of teamwork that the team and its members control. The aspects are A. The individual affective reactions to the team and its work, a measure of the individual learning and well-being, B. The satisfaction with within-team relationships, a measure of the willingness to work together again in the future, and C. The quality of team task processes, a measure of team effectiveness. The survey, according to Skogstad, provides a measurement of the design process quality from the designer's perspective. Linear regression analysis is used to test correlations. Collaboration patterns are treated as dependent variables in the study and can be viewed as evidence of applied design thinking concepts or designerly methods of engaging. The following are 3 essential ideas that describe the design thinking process: A. Constant participation of end users and customers, B. Interdisciplinary teamwork and knowledge exchange, and C. A prototype culture. The study contrasts performance metrics with team communication signatures that may reflect appropriate conduct in the virtual interaction space of designers, guided by these interaction patterns in design thinking. Key findings. Findings related to hypothesis. Authors evaluated the hypothesis that online interaction signatures of high-performance design teams are notably different from those of low-performance design teams based on the team collaboration networks and performance measurements collected during the case study. Authors were able to find statistically significant relationships between the 11 design teams' online interaction behavior and this assumption. The findings imply that teams that prioritize external communication, team internal knowledge exchange, and diversity in the solution space through iterative prototyping perform better overall. As a result, the data set reveals relationships between independent team performance indicators and email and wiki-based team interactions. See the figure. Figure shows that there is a positive and substantial relationship between average team member happiness and the proportional number of outbound email messages sent by a team. This implies that involving external sources of information, end users and customers, improves team performance. When more independent variables are added to the regression model, the quality of the prediction improves even more. The amount of emails a project team has received from the teaching team is put into the regression equation in a second study. See the figure. Figure shows the average team member satisfaction. According to the findings of the second linear regression study, teams that receive more emails from the teaching team are statistically less satisfied with their projects. The teaching team's remedial involvement in the case of flaws or disagreements in the collaborative process is a valid interpretation of this phenomena. Another investigation of knowledge-sharing behavior focuses on the 11 project's wiki areas. The team collaboration networks store information on when wiki pages were created, modified, and hyperlinked to other project resources. This information provides insight into the organization and coherence of information in a wiki system. With data from the design store services, a graphical depiction of the project wiki spaces was generated. See the figure. Figure shows 3 examples. The structures depict the ultimate topology of a project wiki space, which is determined by hyperlink relationships between wiki articles and various external resources. This basic observation already demonstrates that design teams use wikis in a variety of ways. The 3 teams' wiki networks, theta, alpha, and gamma, have diverse patterns in their resource linkages. Theta and alpha display a vast number of wiki pages, each of which covers a certain topic or theme. Several sites clearly serve as indices to a large number of additional resources, clustering related nodes and acting as hubs for other wiki pages or external information sources. Team Gamma's wiki area, on the other hand, has a rather simple topology. Not only is the total number of wiki pages far lower, but the interconnectedness of the resources is also much lower. These quantitative features of wiki spaces did not disclose statistically relevant relationships to performance measurements. However, certain subscales of the team diagnostic survey show a link between team effectiveness process criteria and observed wiki structures. The scale contributes to the overall measure of the quality of team task processes by grading knowledge and skill-related statements like members of our team actively share their special knowledge and expertise with one another, and our team is quite skilled at capturing the lessons that can be learned from our work experiences. Theta, alpha, and gamma average results of this subscale correlate with the visual perception that the breadth of material provided in a wiki system and enhanced resource connection contribute to the quality of a knowledge-sharing process. This supports the idea that wiki structures can reveal some insights into information sharing behavior and points to the need for a more thorough investigation. Contributions of this study to the knowledge base. This work addresses a research issue arising from the disparity between the informality of creative design processes and the formal needs for computational real-time analysis. Team collaboration networks are a methodology for describing and storing activities in a chronological order during project-based collaboration. The networks can be customized and utilized in a variety of design projects to collect and compare the semantic features of actors and information resources. The outcomes of an illustrative example demonstrate that computational analysis of virtual design collaborative activities is time-saving. The data set revealed significant discrepancies between the online signatures of low and high-performing teams. Contributions to research environment. The contribution of this study to the field of applied design research is a customizable software tool that provides services for the direct and non-interfering analysis of concurrent design operations. Tools and procedures have been developed to aid in the investigation of the ever-increasing range of technologies and phenomena that arise as a result of distributed engineering team activities. The design store technology enables for faster and non-interfering team observations by decoupling data collection from concurrent analysis. The service-oriented approach streamlines the unobtrusive integration of teamwork analysis into present and future research initiatives by automating the recording of remote communication data. The foundation is laid for a revolutionary approach to real-time team diagnostics. The same service-based methodology that was used to provide insights into communication behavior now opens up new opportunities for assisting design team management. Real-time knowledge of potential downsides and process obstacles is generated with a more detailed understanding of performance-relevant data. This provides new beginning points for the development and implementation of enhanced design process management tools and dashboards. Conclusion of this study. Authors have created a tool for capturing and analyzing multimodal team interactions in technology-enabled creative spaces in real time. In a graph-like representation known as team collaboration networks, the Design Store platform provides a technology framework for collecting and monitoring concurrent interaction events and distributed online communication. Over the course of 8 months, the system developed was used in the conceptual design phases of 11 distributed, interdisciplinary engineering projects. The online actions discovered in email archives, wiki spaces, and public team folders have been transformed into team collaboration networks, which serve as a foundation for visual and quantitative analysis of structures and trends in engineering design teams' interaction behavior. Patterns in the online interactions of design teams can imply performance measurements. This is crucial because it shows that objective cooperation measurements can be used to approximate design team performance in real time. The findings of this study support the need for a more thorough examination of design processes in IT-enabled collaboration environments. The outcome provides a technological foundation as well as the initial statistical input to help the present and future research activity in this regard. This study also aimed to broaden the scope of empirical design research by allowing researchers to deal with the rising complexity of design environments. The research advances a novel paradigm for doing real-time design team diagnostics, with implications for design theory and organizational process implementation. Thanks for watching. Comment for any suggestions. Like, share and subscribe for more videos.